Marhaba. Okay, today in this video we want to talk about a relation between two sets, which is the subset relation. Okay, so let's start with two sets. So let A and B be any two sets. Okay, what do we mean by this? We mean that A is a collection of objects, so is B. So a set is just a collection of objects. Okay, we say that A is a subset of B if, okay, A is a collection of objects. We call them the members of A. So A is a subset of B if and only if every element of A is also an element of B. Is also an element of B. Okay, so this is the key point of this video, that we call a set A to be a subset of a set B if every element in A is also an element of B. So I forgot here, if every element in A is also an element of B. Okay, what does it mean? Okay, here is the what we call the Venn diagram. So this is the set B. Say it contains A, B, 1 and 3, and this is the set A. Say it contains B and 3. Notice here that every element of A, what are the elements of A? We have two elements, B and 3. B is an element of A, which is also, okay, so here is B, which is also an element of B, and 3 is an element of A, which is also an element of B. So every element in A is also an element in B. So we can see the set A here. This is the set A. Okay. So in this case, we say that A, in this example, A is a subset of B, and this is the notation we use. Okay. So this is the notation to say A is a subset of B. Okay. Because every element in A, okay, B is in A, which is also in B, and 3 in A, which is also in B, and these are all the elements of A. Okay, because every element in A is also in B, we call A to be a subset of B. Okay, so how do we write a subset is a subset of B in predicate logic? We say for every object X, if X is an element in A, then it is an element in B. Okay, this says, look, what does this say? This is a universal quantifier. Every element X, if it is in A, then it is in B. Okay, this is exactly the meaning of A being a subset of B. Okay, and again, the Venn diagram is, this is B, and this every element A is contained entirely, or every element in A is also an element of B. Okay, let's think, what does it mean? What is the negation of this sentence? What does it mean that A is not a subset of B? Well, it means it is not the case that every element in A is an element in B. So it means there is some element X where X is in A, and X is not in B. Okay, so this is the picture. We have the set B and we have the set A. This is the set A. A is not an element, is not a subset of B, because not every element in A is a subset of B. For example, here there must be some elements. Okay, maybe there are elements which are in both, but there are elements in A not in B. Okay, we only need one. Okay, let's call it star. Since star belongs to A and it doesn't belong to B, then this statement is not true, and so not every element in A is in B, and so A is not a subset of B in this example. Okay, note that we can use our identities in logic, our equivalences in logic, to go from here to here. Okay, so you can, okay, A is not a subset of B. okay, is logically equivalent, not the, what is the meaning? This is the negation of being a subset. Being a subset means every element X, if it is in A, then it is in B. Okay, sorry. Okay, now look, let me say one comment here is that X belongs to A is a statement. Okay, it states that X is an element in A. It's a proposition, it's a predicate. X, like X has this property if it's an element of A. So this is a predicate implying another predicate. Okay, X belongs to A is a statement, which will become a proposition once we substitute a value for X. And this is also a predicate. This is having the X have this property if it belongs to B. Okay, so let's continue. So this is equivalent to not being subset, and this is equivalent to there exists an X, not X belongs to A implies X belongs to B. Remember, when the negation jumps over a universal quantifier, it gives us a existential quantifier, but it means it's not the case that every element has this property. It means there is at least one element which doesn't have this property. Okay, now let's see, there exists an X, not, we know an implication is logically equivalent to the negation of the hypothesis, so X doesn't belong to A, or the conclusion. Okay, so you may think of this, the hypothesis P, and this is the conclusion Q. So this is P implies Q. P implies Q is logically, I'm talking about this equivalence. P implies Q is logically equivalent to not P or Q. Okay, now we use De Morgan's law. Okay, there exists an X, and now the negation of a disjunction is the conjunction of the negations. So what is the negation of this? X belongs to A. Conjunction, negation of this, X doesn't belong to B. Okay, see, A is not a subset of B is logically equivalent to finding some X which belongs to A and doesn't belong to B. And this is what we wrote here. So you find an X, here it is star, which belongs to A and doesn't belong to B. In this case, A is not a subset of B. Okay, because not every element of A is also an element of B. Okay, let's have examples of subsets. Okay, for example, look at this set. This is a set containing one element, which is the number 1. This set is a subset of this set of 1, 2, of the set containing 1, 2, 3. Right? Why? Because every element here is also here. We only have one element, which is 1, and 1 also belongs to the other set. Okay. Now this set, the set containing 1, 2, 3, is a subset of the set of natural numbers. Okay, why is this? Because every element here in this set, okay, which are the elements 1, 2, 3, are also natural numbers. Because what are the natural numbers? These are all whole numbers starting from 0. Okay, so 1 is also in the natural numbers, 2 is also in the natural numbers, 3 is in the natural numbers. So every element here is a subset of this set. Now, the set of natural numbers is a subset of the set of integers. Why? Because every natural number is also an integer. And every integer is a rational number. So the set of integers is a subset of the set of rational numbers. Why? Because it chooses any integer n in z. Okay, then, so if n in z, then n is of the form n over 1. So it belongs to Q, the rationals. We define the rationals to be all numbers of the form an integer over an integer where the denominator is not 0. Okay, so if n is an integer, then it is also n over 1 is also n. Then n is also a rational number. Now every rational number is a real number. So the set of rational numbers is a subset of the real numbers, and every real number is a complex number. So the set of real numbers is a subset of the complex numbers. Okay, why? If you choose if x, okay, you remember we can, instead of saying if then, we can use the arrow. So if x is a real number, then, so this is if then x can be written in this form, x plus I times 0. And we know that this is a complex number. So this is a number in the complex sets, in the complex number set, in the set of complex numbers. Okay? Remember, we defined the set of complex numbers to be all numbers of the form x plus iy such that x and y are real numbers, and I is square root of -1. So x is a real number here, and 0 is a real number. So here x is x and 0 is y. Okay. Let's have an example, another example. Let P be the set of prime numbers. Okay, so this is the set of, okay, how do we write this using our set notation? We say this is the set of all integers n, even we want them to be positive, all positive integers, such that n is prime. Okay, so let this be the set P. Remember, this says P is the set of all positive integers n such that n is prime. Okay, and let D be the set of all positive integers such that n is odd. Okay, so P is the set of prime numbers, D is the set of positive odd integers. Okay, clearly P is not a subset of D. Why? Because there is some element here in P which is not in D. In other words, there is some prime number which is not an odd integer. Okay, namely 2. 2 belongs to P because it's a prime number, but 2 doesn't belong to D because 2 is not odd. Okay, so what is the picture here? We have, this is D, say, it contains, and this is P. Okay, now in, for example, P contains 3 because 3 is prime, but also D contains 3 because 3 is odd. They also contain, both contain 5, both contain 7 because 7 is prime and odd. They contain 11, 13. Okay, now the number 1 is here and the number 9 is here because 1 is odd but not prime. 9 is odd but not prime. Okay, but we now look at 2. 2 must be here. 2 because it's a prime but not odd. So this shows that we found an element which is 2, which is in P but not in D. So this means that P is not a subset of D, because P being subset of D means every element in P is also in D. But it's not the case. There is at least one element, which is 2, which is in P because it's prime, but not in D because it's not odd. Okay. Let's take another example. Okay. Look at this. Let's look at the set V. And the set V has the elements 3, 1, x8, x and 8 and u, and the set containing 3 and x. Okay, and the set W, sorry, the element W, the letter W, and the set containing Z and 4, and finally Z. Okay, so how many elements we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So V has 9 elements. Okay, notice that 3 is an element of V, right? Because where is 3? Here is 3. Also notice that U is an element of V. Why? Because U belongs to V. It's one of the elements of V. Okay, 4 is not an element of V. Why? Because none of the 9 elements are 4, is 4. Okay, so the first element is 3, it's not 4. The second is 1, it's not 4. This is x, not 4. This is 8, this is u. This is the set 3 and x, containing 3 and x, it's not 4. This is w. This is the set containing z and 4, it's not 4. And the last one is z, it's not 4. None of them is 4. So 4 is not an element of the set V. Okay, notice that the set containing 3 and x is an element in V, right? Because here it is. This element is the set containing 3 and x, and so it's an element. Okay, at the same time, this set is also a subset. So 3 and x, the set containing 3 and x is a subset of V. Why? Because every element in this set is also an element in V. Okay, what are the elements in this set? You have 2 elements. They are 3 and x. We need to see that 3 is an element of V and x is an element of V. Well, 3 is an element of V. Where is 3? Here it is. Also, x is an element in V. Here is x. Okay, so because every element in this set is also in V, then this set is a subset of V. Okay, again, this is a subset because every element here is also an element in V. 3 is an element here and it belongs to V. X is an element here and it belongs to V. Okay, let's see more examples. Look at the set containing z and 4. Okay, this is an element in V. Right? Here it is. This element is a set. Okay, you think of a set as one object. It's a bag containing z and 4. This bag belongs to V. So this is how we write. This whole thing is an element in V. Okay, this set z and 4 is not a subset in V. Okay, why? Because not every element in this set is also in V. Okay, for example, let's check them one by one. Okay, z is an element here. It is also an element here. But 4 is an element here. But 4 is not an element in V. None of them. We discussed this. None of the elements are elements in V. Okay, so this shows that the element 4 is an element of the left-hand side set, but it's not an element of V. And therefore, this set containing z and 4 is not a subset of V. Okay. Now, I'll leave this lemma. Lemma means a small theorem. I'll leave it for you to prove that if A and B are sets, then A is equal to B if and only if A is a subset of B and B is a subset of A. Okay, remember, here this is an if and only if statement. It's a biconditional statement. You need to prove the forward direction, which means if A is equal to B, then A is a subset of B and B is a subset of A. And you need to prove the reverse direction, that is, if A is a subset of B and B is a subset of A, then A is equal to B. Okay, let me discuss the first one quickly. Assume this is true, so we will do a direct proof. Assume A is equal to B. What does it mean that two sets are equal? It means they contain the same elements. Now we need to prove a conjunction, which means we need to prove 2 things. To prove a conjunction is true, you need to prove this and that. Okay, let's prove this. We want to prove that A is a subset of B, which means you need to show that every element in A is also in B. So choose any element in A, but we know that B contains the same element as A because we assume they are equal. Then this element in A is also in B. So A is a subset of B. And you do this similarly, and this the second direction, the reverse direction, says that if every element in A is also in B and every element in B is also in A, then A and B contain the same elements. That is, they are equal. Okay, you can prove it by contradiction, for example. You can, okay, you can assume the hypothesis to be true, and now you need to show that this is true. Okay, so suppose it is false and get a contradiction. Okay, now let's discuss quickly important subsets of the real numbers. Okay, so here is the set of real numbers. What does it mean? What does it mean for A to be a subset of the real number? It means that every element in A is a real number. So you think of A as a set collecting real numbers. Okay, famous subsets of real numbers are called intervals. And let me tell you what are these intervals. Okay, here is the set of all real numbers. Okay, suppose this real number is A and this real number is B, and we collect all the elements between A and B, including B but not including A. Okay, so this set is described as follows. We use a round bracket A, comma, B, and then square bracket. So this is, we say this is the interval of all real numbers. So this is the set of all real numbers. So the set of all real numbers x such that x is strictly bigger than A and less than or equal to B. Okay, so the square bracket is used when we have equality, and the round bracket when we have strict inequality. Okay, so notice that this set is a subset of R, because every element here is a real number. If you choose any element in this set, it will be a real number. So every element of this set is also an element of this set. Okay, you can, so for example, what does it mean to have the closed interval AB? This is the set of all real numbers such that x is bigger than or equal to A, because we have a square bracket here, and less than or equal to B, again because we have a square bracket. So here you have, this is the real numbers, and then you have A here, B here. We collect all real numbers from A, including A, up to B, including B. So all of these numbers, we put them together in one bag, and this one bag is a set. Okay, we denote it by A, B square brackets. Okay, again, you should see that the interval from A to B, including A and B, is a subset of the real numbers. Okay, for example, like using this notation, check that the interval from 2 to 3 is a subset of the interval of real numbers from 0 to 4. Why? Because every element here is also an element here. Okay, so choose an element in this interval, let x belong to this set, to the left-hand side set. Okay, we need to show that x is also on the right-hand side set. Okay, what does it mean to be in the left-hand side set? X is in this interval, so it means that x is strictly bigger, is less than 3 and strictly bigger than 2. But we know that but we know that 3 is strictly less than 4 and 2 is strictly bigger than 0. So this implies that x is strictly bigger than 0 and strictly less than 4. But if x is a real number between 0 and 4, this means that x is an element in the interval 0, 4. Why? Because this interval, we defined it to be the set of all real numbers x such that x between 0 and 4. Okay, since x satisfies the membership condition. Remember, this is the membership of this set, that you should be between 0 and 4. Since x is between 0 and 4, then it's an element. So we prove that every element of the left-hand side, x, is also an element of the right-hand side. So this means that this interval is a subset of this interval. Okay, in picture you have, this is R, this is the interval, this is the interval from 2 to 3, say. So this is 2 to 3, but not including 2 and not including 3. This, all the real numbers here, or every real number here, is also a real number in the interval from 0 to 4. Okay. Let me put it in green. So, and not including 0 and not including 4. Okay, so 0 is not including, we use an open circle, empty circle. So the green one, okay, the green one, okay, I'm saying that the red set is a subset of the green set, because every element in the red set, which is from 2 to 3, is also an element in the green set, which is from 0 to 4. Okay. Now let's have the following theorem about sets. Okay, the theorem says that if you choose any set you want, so let S be any set whatsoever, then we know two things about this set, that the empty set is a subset of the set S, and 2, the set S is a subset of itself. Okay, so we need to prove these two statements. So prove. Let's prove the first one. So again, what is the theorem is telling us? That the empty set is a subset of any set, and any set is a subset of itself. Let's see. Let's prove the first one. So what does it mean to show that the empty set is a the empty set being a subset of S means that the following statement is true, that for every object X, if X belongs to the first set, then it belongs to the second set, right? Remember, we defined A to be a subset of B if every element of A is an element of B. So to say that the empty set is a subset of S, it means every element of the empty set is also an element of the set S. Let's see that this statement is true always. Why? Okay, this is a universal quantifier. It means choose any arbitrary object you want. So now look at this, the hypothesis. This is a conditional statement. Okay, look at the hypothesis of this conditional statement. It says that the object X belongs to the empty set. Okay, this statement is always false. Why? Because the empty set contains no elements. So we are saying the object X is contained in the empty set. But this is a false statement because the empty set has no elements. So this is a conditional statement with a false hypothesis. This means that this whole conditional statement is true. Okay, whenever the hypothesis of a conditional statement is false, the whole conditional statement is true. So this means for every object X, this property is always true. So the whole thing, the whole statement is a true statement. Okay, and this means that, what is this statement? This is what it means for the empty set to be a subset of the empty set. So we are saying every element of the empty set, which there are none, is also an element of the set S. Okay? So this is, if you want, this is a trivially true statement, because phi has no elements to check. We need to check that every element in the empty set is also an element of the set S, but there are no elements in the empty set to begin with. Now, the second point says that S is a subset of S. What does it mean that S is a subset of itself? We need to show that every object X, if X is an element of S, then it is also an element of S. Well, this is a direct proof. Choose any element, any object X. Suppose this is true. If X belongs to S is true, then X belongs to S is also true. So if this is true, then this is true. So we proved whenever the hypothesis is true, then the conclusion is also true, which means that the whole condition statement is true. So for every object X, X has this property that whenever it is an element of S, it is also an element of S. In other words, every set is a subset of itself. Okay. Now let's see. So this means that when S is equal, sorry, forget about this. Let's now we want to say what does it mean to be a proper set. Okay, so we say that a proper subset. A is a proper subset of B if two things happen. If first A is a subset of B, this means that every element of A is also an element of B, and A is not the whole of B. Okay, so A is not equal to B. So when A is a proper subset of B, we write A, this symbol B, okay, without the equality horizontal bar. Okay, so all what I'm saying is that we have B, a proper subset of B, say A, so every element is a subset first, so A, every element of A is also in B, but A is not all of B. This means there must be some element in B which is not in A, because if every element in B is also in A, then they are equal. So there must be some elements here. Okay, so let's write it in logic, in predicate logic. A is a proper subset of B means that A is a subset of B. So how do you write this? That for every X, if X belongs to A, then it belongs to B. So every element of X is also an element of B, and they are not equal. So it means that there exists an X which is in B. So here this is the star. There is an X such that X is in B and not in A, and this X is not in A. Sorry. Okay, so this is the meaning. This means A is a subset in B, and this means that A is not equal to B, because not equality means they don't contain the same elements. Okay, why they don't contain the same elements? Because there is an object X which is in B but not in A. Like in the picture, this is star, or this one, or this one. Okay. Now let me finish this video by just introducing what do we mean by the cardinality of a set. So suppose A is a set and n is a natural number. So this means, what are the natural numbers? They are the numbers 0, 1, 2, 3, and so on. Okay, we say the cardinality of A is n. So the cardinality of the set A is the number n if we say this, if A has or contains n, precisely n many elements, or n elements, if A contains n elements. Okay, in this case we write the cardinality of A by using two vertical bars is equal to n. Okay, So the vertical bar means the cardinality of A is n. Again, what do we mean by the cardinality? We mean the size of the set, or the number of elements in the set. Okay, if this is true, if the set A has n many elements, then we say that A is finite. In this case, A is finite. Okay, for example, look at this set S, and this set S is the set of all integers, positive integers, such that x is odd and x is strictly less than 10. Okay, so what is this set? This is the set of all positive odd integers less than 10. So they are 1 is odd and positive. It is 3, 5, 7, 9, and that's it. 11 is bigger than 10. So only these integers satisfy the membership condition. What is the membership condition? You need a positive integer belongs to S if it is odd and it is less than 10. So among all positive integers, only these 5 numbers are odd and less than 10. Okay, so because S contains 1, 2, 3, 4, 5 integers, 5 elements, we say that the cardinality of S is 5. Okay, so remember, the cardinality is the number of elements in A. Okay, if A has exactly n elements, we say n is the cardinality of A. So S has 5 elements, we say the cardinality of S is 5. Okay, now if A is the set of Arabic alphabet, then what is the cardinality of A? The cardinality of A is the number of elements in A, which means it's the number of Arabic letters, which is 28 letters we have in the Arabic alphabet. Okay, now what is the cardinality of the empty set? Okay, how many elements are in the empty set? Well, the empty set is the set which contains no elements, so we have 0 elements. So we say the cardinality of the empty set is 0. Okay, now sometimes we can't find a natural number n in which A contains n elements. For example, look at the set of natural numbers. It contains 0, 1, 2, 3, 4, and so on. We can't say that this set contains 5 elements, or 6 elements, or 1 million elements, or 10 billion elements. This set, we call it infinite. Okay, and we say it has an infinite cardinality. So this set is infinite, it's not finite. So it's not finite. Because how did we define finite? We said a set is finite if it contains n elements, where n is a natural number. So it's a number from 0 to 1, 2, and so on. Okay, similarly, the set of integers is infinite, the set of real numbers is infinite, the set of rationals, all of these sets are infinite sets. They are not finite, we call them infinite. Okay, because the cardinality of Z is not equal to n for every natural number n. Okay, I mean, we can say that Z, the set of integers, has 1 element or 2 elements or 3 elements. It has so many elements, more than every natural number. So we say in this case it's an infinite set.